Good afternoon. This is Rich Nass with Open Systems Media, and I am here for this week's installment of 5 Minutes With. This week, I will be speaking with Bruce McWilliams, actually Dr. Bruce McWilliams, who is the President and CEO of Intermolecular. Good afternoon, Bruce. How are you?
Very good. It's good to be here.
Good. Well, thank you. Okay, so it's a good thing you have that doctor in front of your name, because we're going to talk about some pretty some pretty complex stuff here that you guys are working on.
Yes.
Intermolecular is involved in the design of materials. So I'm assuming that this is what ICs are made from today. Is that the type of materials that we're referring to?
Yes, that's what the materials needed for making the future integrated circuits.
Okay. So people have been working on this topic for quite some time. Obviously, there's lots of different materials. All the ones that most people are familiar with. There's a bunch that people aren't familiar with. But is there really room for innovation in this space? I mean, aren't you limited by the elements of the periodic table?
There's absolutely room. The periodic table is a big thing, and in the beginning, integrated circuits, there were just a few materials that lasted for a long time, and they were aluminum, silicon dioxide, maybe boron and phosphorus as dopants, and that was what it was in the beginning. And in fact, but as time has progressed, in order for Moore's law to continue, materials innovation has been essential. And it's more essential now than ever before. Maybe the first time this happened in a big way was copper in the late 90s. Aluminum had just run out of steam, and that required a bunch of new materials to make that whole copper system work. And then on with strained silicon, and then we had high K metal gate. And that transition occurred at 28 nanometers, and where things are at now is for logic to continue to progress. If they don't have materials innovation, transistors won't get faster as they shrink, and there'll be more and more loss in the interconnect. So the motivation for higher performance as you go to these more advanced geometries goes away without materials innovation. So in the area of logic, the next big thing will be going to a non-silicon channel, and that will require all sorts of innovation in how you connect to the transistor and how you build the stack on top of the gate stack. Likewise, memory can't progress without materials innovation. DRAM is, in order for to continue to get more and more bits of memory on the DRAM, they have to make the capacitor smaller. And when they make it smaller, they have to still have just as much capacitance and lower leakage, so they have to make a better and better capacitor. And that absolutely requires materials innovation. And likewise, in the non-volatile memory, this new class of storage class memories, where people are talking about literally 1 trillion bits on a chip, 3D cross-point memory, they have to make spectacular. They make the whole memory element in a via that's some 10 to 30 nanometers across, and in that little via they have to have a memory storage element and a selector, both requiring completely new materials.
So if I can stop you there, you said that there was a time where copper ran out of steam. When you say ran out of steam, what does that mean?
Well, yeah, so aluminum ran out of steam. So basically the resistance of the wires was so great that as they shrunk the dimensions and the resistance got even higher, the signal time to go between transistors was increasing. the wires were too resistive. So in order to keep circuits performing better and better, they had to have a lower resistance metal.
Okay. All right. So are there other materials that either you guys are in development with or others, or you're considering that would surprise me?
Yeah, well, I was quite surprised a few years ago to find out about this area of cacalcinites. And these are materials with many different atoms, things like sulfur, germanium, copper, so very complex semiconductors with 5 or 6 different constituents. And there's a very hard space to explore, but in exploring this space, we've been able to find circuit elements with spectacular properties for use of selectors and storage elements in this next class of memory. So the surprise to me was that when you start to put together so many different atom types, that you could find new materials with properties that you essentially couldn't make with conventional silicon kind of devices, and so that's why this space of materials innovation is so rich. By conventional means, people really weren't able to explore a space of this complexity because the number of experiments you would have to do to zero in on what combination is so great that you couldn't optimize these sorts of devices. And today, 4 of the 5 largest memory manufacturers work with us in areas like this because our tools allow them to explore and find these sorts of compositions which are going to enable the next generation memory. And so that Moore's law in the memory space can continue, and the amount of memory you can get on a chip will continue to grow exponentially.
So what's a typical time frame from when you guys are looking into an element and when we actually see that in a manufacturing process?
Well, that's still pretty long. By the time we engage and the customer maybe finds his solution, that can be as short as a year. But then there's the stage of getting that into a production facility, and they have a relatively long roadmap. So I think from the time of a new material we might engage and when it goes into a product, it can be 5 years or more. But it's actually in production. I mean, they could be making test chips and stuff a couple years into it, but the whole process of when you see it in the marketplace, I think 5 years is a good time scale. Maybe
Okay.
DRAM 4.
Very interesting. I'm sure there's lots more we can explore here, but we have used up our 5 minutes. So I would like to thank Bruce McWilliams. He's the president and the CEO of Intermolecular. I'm Rich Nass with Open Systems Media, and I hope you have a great day.
Thank you.